Hello everyone, this is video 1-8, Unit 1, Day 8. It should be watched Monday, 9/19. What are the three conditions for continuity of a function? We do have to have these memorized, so that's why I keep being repetitive about asking us to list them. The first, and it'd be good, guys, if you like paused it and tried to do it by yourself. So try to write these down without me guiding, so you could see if you have them memorized yet. Okay, so if you want to do that, maybe pause it or fast forward this part. But the first condition is that f of a is defined. The second condition is that the limit as x approaches a of f of x exists. And then the third condition is that the limit as x approaches a of f of x equals f of a. Okay, so the limit is the same as the function value. Those are the three conditions. Okay, now we can use these conditions to make a function continuous. So here's an example. Example number 1, find a value of a so that the following function, it's a piecewise function, is continuous. Now x is the input variable. A stands for a constant here, guys. It's a constant that we don't know, but that we need to find in order to make this function continuous. Now when you're doing this sort of thing, making a piecewise function continuous by finding a missing constant, we want to focus on the second condition first, okay? So it's going to go like this. In order for the limit to exist at the endpoints of these pieces of the piecewise function, in order for the limit to exist there, both the left-hand limit and right-hand limit must exist and be equal. So the endpoint of this piece is the x value 3, and then this piece, picks up again there. So the endpoint is 3. So that's where we need to make this function continuous. So I'm going to go x approaches 3 from the left and x approaches 3 from the right. All right? So if x is approaching 3 from the left, I'm on this interval here, so I'm looking at this piece. So as x approaches 3, this part here is approaching 9 minus 1, so the y value is approaching 8 there. Now for x approaching 3 from the right, I'm on this interval, so I'm going to use this piece. So as x is approaching 3, this piece here, just imagine plugging in something very close to 3 for x, we will get very close to 6a. Okay, 2 times about 3 is about 6. So y is going to approach 6a. All right, and if this is unclear to you guys, pause this and try to think about it. Now, in order for the limit to exist, okay, in order for this second condition to happen, the left-hand limit and the right-hand limit must equal each other. So at this point, I'm going to set them equal. And if 8 equals 6a, guys, this arrow thing, this just means if then. In college, I saw this notation a lot, so I'm going to start using it more. But if 8 is equal to 6a, then a is equal to 8 over 6. Then a is equal to 4 over 3. Okay? Now, I'm going to check this. And you don't have to check it, guys, but I think just for our notes we should check it so you see that this in fact did work, because the only condition that we really used right here was the second one. But I'm going to plug in 4/3 for a and then see what piecewise function we actually end up with, and then I'm going to just quickly talk about checking the conditions. Okay, so this part is optional. Okay, but please do this just with me once for the notes. Optional, check. So figuring out that a is 4/3 means that the function is defined as x squared minus 1 for x less than 3. And 4/3 goes in for a, so that's 8/3 x for x greater than or equal to 3. All right, so I'm just going to check the conditions real quick. So 1 is f of 3 defined. Well, f of 3 is going to be on this, so 3 is on this interval here, so I'm plugging 3 into there and I get 8. Check, it's defined. Okay. Now, the limit as x approaches 3 of f of x. I'm going to figure out what that equals. Now remember, 3 is an endpoint for this piecewise function, so I can use arrow diagrams here. So x is approaching 3 from the left, x is approaching 3 from the right. 3 from the left, I'm dealing with this piece, y is approaching 8. 3 from the right, I'm dealing with this piece, y approaches 8, so the limit is 8, perfect. And then the third condition is that the limit as x approaches 3 of f of x is in fact equal to the function value at the value we're approaching, and we got 8 equals 8, so check. Alrighty, so there it is, guys. Again, the checking part is optional. It's a very good exercise, but when you're on your homework or if this were a quiz or something, you could just stop right there. Okay, let's do another example, and then we'll be done with this video. Okay, so here's the second example. This is again a piecewise function, but it's defined in 3 parts. Find constants a and b so that the function below is continuous for all x. Graph the resulting function. Okay, so a and b stand for some constant. Well, this is just a line. Okay, a is some constant, so this is just a line. This here is a parabola, and then this part here is some other line. So we've got a line, we've got a parabola, and we've got a line. Guys, we're going to talk about this more in the future, but lines and parabolas are themselves completely continuous. Okay, there's no like breaks in them. They're completely like smooth. So if there's any parts here that I've got to make continuous, it's going to be at the end points of the intervals. Okay, so I have to do the same thing that I did here. Okay, this was the other page. I have to do the same thing that I did here for the 2 endpoints. All right, so I've got an endpoint at the x value 4. I've got an endpoint at the x value 9. Those are the values where I have to make sure that the limits exist. Okay, so as x approaches 4 from the left, and then I want x approaching 4 from the right. As x approaches 4 from the left, I'm on this interval, so I'm using the top piece. So y is approaching 4 plus a. And then from the right, I'm on this interval, so y is approaching something very close to 4 in there, makes this very close to 3. Very close to 3 squared is 9. Okay, so I need the limit to exist, so I need the left-hand limit and the right-hand limit to be equal. So I go 4 plus a equals 9, then a equals 5. All right, so yeah, so a being 5 would make from here to here continuous. Okay, now I have to do the other endpoint, which is 9. So x is approaching 9 from the left, x is approaching 9 from the right. As x approaches 9 from the left, we're thinking about this interval. So y is approaching 9 minus 1, 8 squared. 64. And then 9 from the right, we're on this interval, so we're going to be using this. So we've got y approaching 9b plus 1. All right, I need the limit to exist, so I need the left-hand limit and right-hand limit to be equal. So 64 equals 9b plus 1. Then 9b equals 63. Then b equals 7. Okay, so we've got, if a is 5 and b is 7, then this function here is continuous, all right? And if you want to check it like we did before on the other page, that's a good exercise. Okay, guys, so this video is done. Now let me think about your homework. Alrighty. 1.8. So this video wasn't very long. Let's have you do page 17 all. Okay, so just numbers 1, 2, and 3. Page 17 all. I'm just writing that down. Okay, guys, I'll see you tomorrow. Bye-bye.